Automatic. Addison.
Precise docking is a key capability for autonomous mobile robots. While Nav2 excels at general path planning and obstacle avoidance, docking often requires more accurate position information than standard navigation provides. This is where AprilTags come in. They're visual markers that help robots determine their exact position and orientation relative to a docking station. In this tutorial, we'll implement automated docking by combining Nav2's docking server with AprilTag detection. We'll mount an AprilTag near our docking station and configure our robot to use it as a visual reference point. The Nav2 Docking Server will handle the approach and final alignment, using the AprilTag's position data to guide the robot into the dock. AprilTags are visual markers designed specifically for robotics and computer vision applications. These tags appear as small black and white squares with unique patterns inside. Their primary purpose is to help robots and cameras quickly determine their position and orientation in space. When a robot's camera spots an AprilTag, it can instantly calculate how far away the tag is, what angle it's viewing the tag from, and which specific tag it's looking at, as each tag has a unique identifier. AprilTags offer several advantages. One, they're inexpensive to produce and can be quickly printed on a plain sheet of white paper. They perform well in various lighting conditions. They also allow for fast detection, an important feature for real-time applications. You may have heard of another type of visual tag used in robotics called ArUco markers. ArUco markers are similar to AprilTags. They look like small, black and white squares with patterns inside, much like AprilTags. However, AprilTags have some important advantages. First, better in difficult situations. AprilTags work better when lighting is not perfect or when part of the tag is hidden. Number two, more accurate. AprilTags give robots a more precise idea of where they are, especially when viewed far away or at odd angles. Faster to identify. Number three, robots can usually find and read AprilTags more quickly than with the ArUco markers, which is important when things need to happen fast. And then finally, fewer mistakes. AprilTags are less likely to be confused with other objects or misread. Okay, let's get into it. Open a terminal window and let's launch the robot. Remember, I have an alias called Nav, which launches the robot in a Gazebo environment with RViz. So I'm going to write the nav command in AV and wait for everything to come up. Okay, and let's set the pose just to make sure. All good. Looking good. The logs have stopped. Okay, and let's begin by opening a new terminal window and typing this command, ROS2 topic list grep cam _1. So here we can see all of the different topics which are related to the camera. In our depth camera, we can see the depth colored points, 3D point cloud right there. We can see color image raw, camera info is published here. And let's see if we can see the image in a tool called image view. So we need to install it now. I'm going to do sudo apt get install ROS hyphen. And so that we don't have to type Jazzy or humble, you can just do this. So do the $ and then capital ROS _ distro. Okay, the ROS distribution hyphen image hyphen view. So install it. This is a very good tool to view images. Okay, it says, do you want to continue? Y and then enter. Let that install. Clear. And now to run the image viewer, we're going to do ROS2 run image view and then do image view and then do -- ROS -args space -r image, and then the assignment operator like that, and then cam_1 / color / image _ raw. Enter. Okay. So this is the screen that pops up. And now let's move the robot to some area where it can see something, because right now it's just a gray image. Not super exciting, but let's click Nav2. And shall we just look at the file cabinet? Let's go and do that now. Over here. Do it to an area that's just in front of the file cabinet. So robot moving. And here is our, actually this is a cafe, so it's probably just an area for holding food. Okay, and our robot is turned and looking at it now. Bunch of shelves. Okay, it's twisted a little bit so you can see what the camera sees. All right, so our robot is looking at this compartment that has a lot of shelves. Let's go over to RViz, and we can see here in RViz with the image viewer that we're now seeing the camera, what the camera sees, and looking at that same compartment with shelves. So that's looking through the front camera, only camera really, of the Yaboom Rossmaster X3. So this camera image is very important because it's going to be useful for AprilTag detection. And we're going to need to process them through a package called, and let's bring this up. I'll show you here. The Google is going to need to use a image _PROC ROS2 package. It's called image proc. Here's the big ROS2 wiki on it. Okay, it sees all, you can see the different information that it subscribes to and that it publishes to. So the image proc package, which we're going to use, it's going to subscribe to this topic. Let's go back to ROS2 topic list. Let's do that grep again. ROS2 topic list. Do that. And then let's do grep cam_1. Okay, so the image proc package, which we are going to deal with in a little bit, is going to subscribe, okay, to the image raw data and the camera info right here. All right, and then we're going to publish a image rect. I'll show you here. Let's go over here. Image rect, right there. We're going to do cam1 color image rect is what we really want, a rectified image. Okay, that's the goal. That's the end goal. Now, why do we need this step? Why do we need a rectified image? Why can't we just use the raw image? Well, for AprilTag detection, we need to use rectified images, which remove camera lens distortion. The camera lens naturally bends the image a bit, like looking through a curved glass, which can make the square tags look slightly warped. So the rectification right here fixes this so that the tags are easier to detect. And with our rectified images ready, we will use the CPU-based AprilTag ROS package. So let's go take a look at that. AprilTag ROS package. And you can see it takes as input this rectified image. Okay, which takes out all the camera lens distortion, and that's what we need as input to the AprilTag 2 ROS package. Okay, and this subscribes to the rectified image and the camera info, and it's going to publish transform and tag detections. Okay, and the tag detections are a specific message type. I'll show you here. AprilTag messages, message AprilTag detection array. this message type right here is going to be published by the AprilTag ROS package. That's our goal, the detections and the transforms as well. Okay. And if you don't want to use, if you want to use a GPU accelerated AprilTag ROS package, you can use the Isaac ROS AprilTag package right here, which is GPU accelerated. But we're not going to be using that in this because we're using a virtual machine. So we're not using this. But for a production application, you might consider this. Okay, you can see the different subscriptions and publishing that it does. All right, so once we've got the detections, we are going to use the Nav2 Docking Server. Let's go to Nav2 Docking Server. Okay, and let's see here. It's got some good documentation on the Nav2 Docking Server right here. All right, and what this is going to do, it's going to subscribe to the detected docking pose. Okay, the current pose of the dock, and that's what it's going to use to be able to navigate your robot to the docking station. So that is what we're going to do. That's the whole pipeline. All right, so now that we've got all of that theory out of the way, we need to create a new package. Let's do that now. Okay, let's create the new package. You're going to CD to the workspace, source, Yaboom ROS master. And let's create the package. You are going to put this command here. ROS2 package create -- build type ament cmake -- license BSD 3 clause, and then maintainer name Ubuntu, and then maintainer email, and then automatic Addison@todo.com, and then Yaboom ROS master docking. Enter. Okay, we've created our package, and now let's edit the package XML file. Oh, we have to go into it first. That would help. Get it, package XML. And let's take a look at here and see what we need to update. So let's go over and have a look. So the first thing we need to do, now that you've got that open, is you need to add a good description. And you can add pretty much whatever you want, but I'm going to say here, contains the core files related to docking using AprilTags and Nav2. Save it. And down below, under the build tool, let's add our dependencies. So I'm going to put that here. And we've got different dependencies: the AprilTag ROS, AprilTag messages, image proc, image view, Nav2 simple commander. Save it. Now let's head over to the CMake lists. And you need to make sure that this package has the dependencies as well that you're going to need. So I want you to see this area that says find dependencies and put this here. All this block right here, iment CMake Python, all the way down to TF2 ROS. Make sure you have that there. And once you've done that, save it, close it. Go over to the meta package, cd ... And let's do cd Yaboom ROS master. Let's get it CMake. Actually, no, let's do get it package first. Okay, make sure you've got this docking piece right in here. Yaboom ROS master description, Yaboom ROS master docking. Make sure you have that in the package XML. Just have a look at CMake and see if yeah, okay, that's fine. Keep CMake list as it is. Now build your workspace. So CD, let's open up a terminal to do the building. CD ROS2, ROS dep install -- from paths src -- ignore -- source -r and then -y. Okay, all my required dependencies are already installed, but you might have a prompt that prompts you to install the AprilTag ROS package or image proc. Just type in your password, press enter, and then you also get this message as well. This all required ROS steps installed. Now, before we move forward, I just want to make sure that your ROS2 camera data, your Gazebo camera data, is published to the correct topic, to correct image frame ID, sorry. So we're going to go to CD Yaboom ROS master description, clear, CD URDF, CD sensors, and let's have a look at our RGBD camera. Okay, so we can see that we are not publishing the data to the correct frame. So let's go over to what's currently on GitHub. It's correct on GitHub. I always have the latest code over there. And let's go to the latest URDF and let's make that correction. So I'm going to highlight all of this. We want the camera image data to go to the optical frame, the camera optical frame by convention. So I'm going to copy all this and let's Control V in there and save. So we fix that, close out everything. Now we need to make sure you add the AprilTag to your cafe world. So let's do that now. Your cafe Gazebo world. So CD ROS2, CD ... CD ... CD Yaboom ROS master Gazebo. Let's go into the models folder and type dir. And if you go to the very top, we can see our AprilTag model right there. There it is, AprilTag 3611 and then 5 zeros. Remember that name, because this is where your system is going to look for. And this folder is where your system is going to look for all of the models, including the AprilTag model. Now let's have a look at our world. So CD worlds. Okay, and then let's have a look at the cafe world to make sure that the AprilTag is there. It is in fact there, and the model name matches what we had in the models folder. Okay, you have the name that you put, the position, orientation. So this is X, Y, and Z location in the world. The roll, pitch, and yaw, that's rotation around X, rotation around Y, and rotation around Z. And then if the model is static or not. Static means the model does not move in the environment, and the AprilTag will just remain in the same location. So that's what we want. Save the file and close it. Let's have a look at it. So type this command right here. I'm going to copy and paste it because it's kind of long. So that's it. Export the Gazebo sim resource path, the path to the models folder. Put that in your terminal, and when you're ready, press enter. This tells Gazebo, where are your models located? And now let's have a look at the cafe world. So gzsim and then cafe.world. Let's have a look. Bring it up. And I love how quickly Gazebo moves when you're not running anything. So let's go over here and let's zoom in. Pretty cool. So there we go, right there. Our AprilTag in all its glory. And remember, you can adjust the pose as you needed to ensure it's visible and correctly placed in your specific world layout. And in a real robotics project, you'd actually just print it out and place it on a wall. Let's close it. Control C. Okay, now let's create a launch file. So What we need to do in this section is we need to convert the raw camera images into rectified images. These are images without curvature. It's like the ideal camera image. And so we're going to create a launch file that's going to have a node that's going to subscribe to the camera information, the raw image, and output the rectified image. So that's the goal in this section. So we're going to go to CD. Let's go to ... CD ... Okay, and then CD Yaboom ROS Master Docking. We're in here right now. And let's do make dir launch. And while we're at it, let's do make dir config. This is where our configuration parameters for our AprilTag will go. Okay, and let's add a launch file inside the launch folder. Let's do get it AprilTag doc pose publisher dot launch. Spell it correctly. So AprilTag doc pose publisher dot py. Open it up. Go to my GitHub. I've got it cloned here into my downloads folder. Let's have a look. Launch. Open this puppy. Control A, Control C, and then Control V. And let's comment out right now anything we don't need. So we're not going to be using the detected pose publisher just yet. Anything else? Think we're good. Everything's good. Let's save and close. Okay, so we have that, and we need to edit our cmakelist.txt for the Yaboom ROS Master docking package. Okay, and we added 2 new folders, so let's add that just below this piece. So we've got config and launch. Okay, and while we're at it, let's add the configuration parameters. We're going to cover that in a bit, but I want to show you how to do that. So let's go to downloads, Yaboom ROS Master, docking, config. We need to add this folder. So I'm just going to add it directly. Just create these folders, ROS2, source, Yaboom ROS Master, docking, config. And let's just copy this and let's paste it over into where we want it to go, right in here. So Yaboom ROS Master docking config, and here's our YAML file parameters for the AprilTag. Don't worry about what all that is right now. I'll cover that in a bit. Let's close it. Okay, and save everything. Everything's good. Let's open up a new terminal window, and we need to build. So I've got the build alias. Okay, and let's just show you that now because we're going to run this again and again. So the build alias CDs into your workspace, runs colcon build, and then sources the bash all in one line. So I'm going to do build to build everything. Now we close everything here. Let's launch the robot. Let everything come up. Okay, and let's set the pose. Good pose. Open a terminal window, and let's launch that AprilTag Pose Publisher launch file. So ROS2 launch, Yaboom ROS Master docking, AprilTag. Nope, not that. AprilTag doc Pose Publisher. AprilTag Dock Pose Publisher. Why aren't you launching? Let's have a look. AprilTag Dock Pose Publisher. Let's have a look. See what's going on. ROS2 source. ROS master docking. Launch. AprilTag Dock Pose Publisher. Oops. We made a mistake. It's .launch.py. Okay, .launch.py. So we've got to close everything. Sorry about that, folks. Actually, no, actually, I don't think we do. Let's just build. Build again. Okay, because we've already got the robot open. Let's try running it again. So ROS2, launch, Yaboom ROS master, docking. Okay, and then AprilTag underscore dock. Underscore, let's see, let's source the bash. Okay, ROS2 launch, Yaboom ROS master docking, and then AprilTag dock pose publisher .launch.py. Not working. All right, so let's go back here. Go to ROS2 source, Yaboom ROS master docking, launch, AprilTag dock pose publisher .launch.py. Looking good to me. Looking good to me. How about we just clean everything out? So remove RF, build. Be very careful with this. Install and then log. Okay, and let's build it all again. From scratch. All because of my fat finger mistake and not putting .launch.py. So robot is still in the navigation mode. So let's give it a shot. And if that's not, I'm going to close everything down and restart everything. This is part of robotics, folks, showing everything. Doesn't always work on the first try. We try again. And we never give up. That's how we do. Let it build. Build, baby, build. Whew, everything is complete. Let's try it now. ROS2, launch, Yaboom ROS master docking. Okay, and then AprilTag. AprilTag. Dock. Still not going. Maybe I have something wrong with my CMake. Let's check that out. CD Yaboom ROS master. CD Yaboom ROS master docking. CD launch. Let's see, get it. CMake. Got the launch in there. That is fine. CD launch. Oh, see the issue? Another fat finger mistake. So let's do move AprilTag dock pose publisher to AprilTag dock pose publisher dot launch dot py. Okay, build again, folks. That's why slow is smooth, smooth is fast. When you move slowly, you make fewer mistakes. Now, okay, we've got navigation running. Let's try it. Maybe third time's a charm. So ROS2 launch, Yaboom ROS master docking. And please run this launch file. Okay, there we go. Run it. That's what we want. That is what we want. And let's check a look at the rectified image. So we do ROS2 run image view hyphen hyphen ROS hyphen args space hyphen R image assignment cam _1 / color / image _ rect. Okay, there we go. This is our rectified image. And now let's take a look at the raw image. Let's go over here. We're going to continue. Image raw. So we're going to do ROS2 run image view, ROS args, and then image raw. And here you should see, so we've got image raw and image rect. Okay, let's minimize all that. So image raw and then our rectified image right here. So if everything is working properly with your system, okay, we launched navigation and then we ran the launch file that we created. Okay, and we had a little trouble because we had the wrong name. So it's going to be image rect and image raw. There you go. All right, that's how you know everything is working. And let's do ROS2 topic list and then this pipe symbol and then grep cam _1. And here we go with the topics. All right. And you should have a topic cam1 detections. We're going to get to that a little later. But the important part of this section is that you have this rectified image. Make sure you've got cam1 color image rect. Make sure you have that topic published. If you've done that, you've successfully completed this section. Now press Control-C to close everything down. And close the terminal window. Let's make sure everything's closed first before you close it. Okay, Control-C and close. Okay, we will now use the AprilTag ROS package to publish the pose of the AprilTag with respect to the camera's optical frame. Specifically, we will detect our tag ID 0, from the family 36H11 in the rectified camera image and then publish the following coordinate transformation. I'll show you here. So we're going to do this. We're going to do parent frame is going to be cam1 depth. You don't need to type this. Optical frame, that's our parent frame. Okay, that's the parent frame. And we are going to do the transform to the child frame, which is going to be tag 36H11 and then 0. That's the AprilTag frame. Okay, so it's the tag, the AprilTag family, which is 36H11, then a colon, and the tag ID. So we want to get that transformed. So we know where is the AprilTag with respect to the camera optical frame, the coordinate frame of the camera. So let's start by doing the configuration file, CD, ROS2, source, Yaboom ROS master docking. Okay, and let's go check this out here. CD config. All right, let's do get it AprilTag. And here is our YAML configuration file right there. Okay, that is what you need. So make sure you have that. Now go cd ... and do get it cmake list.txt. And we've got the config and the launch folders. So close it. Let's open up a new terminal window. Now let's cd to the workspace. Let me run a colcon build and source bash RC. All right, and clear. Now let's run nav. Nav launches the robot. Start that now. Let your robot get up and running. Okay, and let's set the pose. And open up a new terminal window. And let's launch this. So ROS2 launch, yeah, boom, ROS master docking. And then AprilTag dock pose publisher dot launch dot py. Start running it, baby. Run it. Run it. Don't worry about these warnings right here. It's all good. All good. All right, let's see. Now let's navigate to where our AprilTag is. Our AprilTag is over here against the wall. So let's go zoom in. Zoom, zoom, zoom. Let's do Nav2 goal. And somewhere around here. Let's have it going this way to the left. Robot is going to move. Watch it move. God, I absolutely love the movement of mechanism-wheeled robots. They just glide so smoothly. I just love that sideways movement. So cool. Okay. Actually, that was a pretty good. Pretty good. I think it should be in the camera. Okay. Let's see if we're actually getting detections. Okay, let's go into here. Let's clear this. And I want to see what the camera sees. So to do that, we need to use the command to see the camera. So let's take a look at that. I'm going to do ROS2 run image underscore view. Image underscore view hyphen ROS hyphen args hyphen R and then image and then assignment / cam underscore 1 / color / image underscore rect. Okay, we can see the AprilTag. I want to try to get it in the center here of the frame. Let's see if we can do that. Let's use this and turn it just a little bit left. Just a little bit left. Let's see how it looks now. That's perfect. Right in the center of the frame. Right at the bottom. All right, so go here and Control C. You can close that. So what should we do now? How about we check the AprilTag detections data? So I'm going to clear here. I'm going to do a ROS2 topic echo / cam underscore 1 / detections. Okay, here are detections. Okay, and these will pop out whenever your robot camera sees the AprilTag. So these messages include the information about the tag's ID, position, and detection confidence. So let's take a look at it now. There we go. So we've got the camera 1 depth optical frame. We've got the tag family, the ID, confidence, so forth. Some other good information. All right, and let's take a look at our coordinate frame. So I'm going to do CD downloads. Let's remove RF frames. Okay, let's clear. Let's do ROS2 run and then TF2 underscore tools and then view underscore frames. Okay, and let's do events frames, that PDF, so we can see the coordinate frames. And when we expand this out, you can see the AprilTag right here, okay? And you can see it is a child of the Cam1 depth optical frame. So this is a very, very good coordinate transformation because now we can actually calculate where the AprilTag is with respect to the camera's optical frame. Not only that, but we can determine where the tag is with respect to any coordinate frame using mathematics. Powerful tool. That's why I love TF. Really cool. Really cool tool. And let's run it now. Let's see if we can see what is the position of the AprilTag, okay, with respect to the camera 1 depth optical frame. So let's do ROS2 run, TF2 underscore ROS, and then TF2 underscore echo, and then cam underscore 1 underscore depth underscore optical underscore frame, and then space tag 36H11:0. Here we go. So what we're looking at right now is we are seeing the orientation and the position. So the position and the orientation of the AprilTag relative to the camera's optical frame updating in real time. In real time. So let me explain what this data means. Let's just Control C so it's not rolling. Let's explain what this data means. So the camera optical frame, okay, the camera optical frame. Remember from our very first lesson, okay, the camera optical frame is such that the x-axis, so imagine we're in front of the camera. So let's go here. Let's open up the Yaboom. Yaboom. ROS Master X3. X2. All right, let's press enter. Open image, open link in new tab. Okay, you can see that. See the camera in the front, although our camera's a little bit different. So imagine, you have to imagine this because I don't have the coordinate frames drawn on here, but this is the camera's optical frame. We're in front of the camera looking directly, we're in front of the robot looking directly at the robot, looking directly at the camera. So the camera optical frame's x-axis, okay, the x-axis points this direction to the left, you know, to our left, as looking here. The robot's right side, our left side, points this way, starting here and then pushing outwards to the left. That's the x-axis to the side. The z-axis points outwards from the camera lens, kind of towards us, outwards from the camera lens. The positive z points outward from the camera lens, okay? And the positive y-axis points downwards to the ground, downwards, like that. Remember the right-hand rule, okay? So maybe you can draw this. So y points down, x points out to the side, and then z points out of the camera frame, okay? So it's good to get out some paper and write that down. Now let's go over to the AprilTag. Okay, it's better to just go back to Gazebo. So let's go here. So here is the AprilTag. I'm trying to zoom in so you can see it nice. Okay, so for the AprilTag also has its own coordinate frames, and we're looking directly at the tag okay, right here against the wall. And let's look dead on at it right there. So the Z-axis for this AprilTag points towards the camera, towards us, towards the robot, as towards us. Z points out of that tag, away from the wall. The X-axis points to the right of the tag, Okay, so again, use the right-hand rule. Okay, the right-hand rule. So the Z points outwards. Okay, so take your thumb, points outwards, out from the wall. The X-axis points to the right of the tag. The right points this way, the right. Actually, our right, the tag's left. So X-axis points this way. From left to right as we're looking on here. Left to right. Positive X-axis along the wall. Okay, and the Y-axis points up along the tag towards the ceiling. Up along the tag towards the ceiling, along the wall. Okay, remember, right-hand rule, so you can visualize this. Okay, so now that you've gotten the coordinate frames, you understand the coordinate frames for the optical frame and the AprilTag, okay? We need to go back to the terminal so I can interpret these values. So what does this mean, okay? What does this mean? This tells us the tag's position, the AprilTag's position relative to the camera optical frame, okay? Assume we are looking through the camera lens at the AprilTag. We're looking through the camera lens at the AprilTag, okay? So let's just start with something simple. We see that X is equal to 0, okay? What does that mean? What does that mean? That means that the tag, the AprilTag, is slightly left of the camera's center. So again, let's go back over here and let's start. Let's go here and let's visualize the camera again. All right, I'm going to bring up that camera image again so you can see, so we can just walk through this slowly. There's no rush, guys. We're just going through this slow and smoothly. So I'm going to open up a new terminal window. And let's do ROS2 run image view hyphen ROS args -r image, then the assignment operator, and then cam_1 /color /image _raw. Okay, this is the image. All right, and let's put this side by side so you can see it. Okay, so here, so you can see here that we have the position of the AprilTag with respect to the camera optical frame. We're looking through the camera lens right here, so we're looking right down the camera lens and outwards towards the wall. So this is 0, okay? This is 0. X is 0. So that's what we expect because the AprilTag is right in the center of the frame, okay, where X is equal to 0. Now let's go to the second value, okay? So Y, the Y. So remember the positive Y-axis of the camera depth optical frame points downwards from the camera towards the ground. So increasing Y as you go down. And that's exactly what we expect. We see that the AprilTag is in the bottom of the camera frame, which is what we expect because we're going down, positive Y direction. Okay, and then Z right here is going outward from the camera frame. So we're 0.76 meters away from the AprilTag. The robot is 0.76, the camera depth optical frame, the camera is 0.76 meters away from the AprilTag, which is on the wall. And you can see here, that's about right in RViz. By the way, each of these squares is 1 meter. Each of these squares is 1 square meter. So we can see it's about 0.7 meters away from the wall, the robot, 0.7 meters away. And that corresponds to this. Corresponds to that. Okay. So hopefully you understand that. Hopefully this is making sense to you right now. You can also see the values right here, which represent the roll, the pitch, and the yaw values, roll, pitch, and yaw. Okay. And this large value of roll indicates that the tag is mounted vertically on the wall. Okay. So I won't go into the details of how we get these rotations and so forth, but that's how we get it. So you're rotating the camera optical frame parent to align with the child tag, and then you're calculating it like that. So that's you're rotating 154 degrees to get to there, but you don't need to go into the details. More important is the position. Okay, so let's go here. Let's close everything down. I really want to hammer this topic again. Let's go to boom. I want you to see the URDF. This would have been better to explain you. So let's take away, add the robot model. Let's show you the coordinate frame. Let's go down here. And let's just add the camera depth optical frame. Okay. So here is the camera depth optical frame. As I said, the X goes out to the side. X-axis goes to the side. This is what you should have written down. Y-axis, the green, goes downwards. And the blue, this blue Z-axis points outward from the optical frame. So positive Z indicates that the AprilTag is somewhere out here. We're measuring from along this Z-axis outwards. Okay. So that's why we had the 0.76 meters. And then we have X is 0. So this is the X-axis, positive X going from the origin outwards. So X equals 0 means it's in the AprilTag is in the center of the camera frame. And then this green line right here is the Y-axis. So increasing values down here, increasingly positive. And I think, what did we have? We had 0.339 right there, 0.339 for Y. So that's why we had the AprilTag was at the bottom of the camera frame, because we go down 0.3 here, it's at the bottom of the camera frame. So know that, folks. So remember that. That's how you can sanity check the values of your AprilTag detection. It's very important you understand that intuitively, because you're going to need it to for setting up any kind of docking solution. Okay, for your robot. That's it for this section. In the next section, we're going to talk about how to make our docking system work with AprilTags. Now, to make our docking system work with AprilTags, we need to create a node that will listen to the TF topic, the transform topic, for the transform between the camera 1 depth optical frame, the parent frame, and the tag 36H11 frame, the child frame. So events, frames, just kind of explain here what we need to do. So our node will listen to this transformation, okay, and then it will take that information and then publish this information as a geometry message, pose stamped message. So I'll show you here. So geometry messages, pose stamped, which is a time stamped pose, position and orientation right here. So listen to the TF and then republish it as a pose. Okay, because that's what the docking server needs. It needs that geometry messages pose stamped message type. So that is what we're going to do in this section. So that is very important because without it, the docking system will not be able to locate and approach the dock accurately. This is what the Nav2 Docking Server needs. It needs it. All right, so to do that, we are going to open a terminal window. Let's go CD. Let's go CD ROS2, source, Yaboom ROS master, Yaboom ROS master docking, and then source. Okay, and let's create our node. So we're going to go get it, detected underscore dock underscore pose underscore publisher dot cpp. So get it, detected dock pose publisher dot cpp. Open it up. Okay, and let's look for the code. Go to my GitHub repository, docking source. Open this puppy up. And here it is. Control C. And let's go over here to get it. Control V. So that's what it does. Publishes the pose of an AprilTag, which is located on or near a docking station. Okay. So we're subscribing to the transformations published by the AprilTag detection system between the optical frame and the detected tags frame. And then republishing these transform as pose stamp messages, because that's what the Nav2 docking system needs to compute the actual docking pose. So the robot can dock automatically to the charging station. So save it. Close. Close. And as we always do, when we add a node, we need to update cmakelist.txt. So let's do cd dot dot clear get it cmakelist.txt. And we need to add our node. Add it now so that the system will be able to detect it. And so underneath the find package section, I want you to add this. Detected dock publisher, source, detected dock pose publisher .cpp, detected dock pose publisher, and then the dependencies. Add this block right now. Pause the video. I'll wait a little bit, give you a chance to add it. Okay, now that you've added it, I want you to save. Now we need to update our launch file, so we do cd launch. Go to get it AprilTag .pose publisher.launch.py, and let's look for anything we need to uncomment here. Detected dock pose publisher. This guy. So let's uncomment this action below. The detected dock pose publisher, whose sole role is to publish the pose of the docking station. Okay, the AprilTag that's above the docking station. Read that transform and publish it in the right message type. That's all it does. Okay. Now we need to build. So let's clear, run build. All right, let's clear. Okay, now what we need to do is we need to edit the launch file. So I'm in ROS2 source, Yaboom ROS master, bring up launch. And this is the main launch file we need to edit. So get it ROS master x3.launch.py. And let's go to the very top, because we want to be able to launch all this docking stuff automatically. So on line 42, I'm going to uncomment this package share docking. Let's just go from the top. Let's go through. Slow is smooth, smooth is fast. Line 51, let's uncomment that. Just going through. This is the same launch file from the GitHub. Let's uncomment this line 254, this start AprilTag dock. This is what we want to start. Looking good, looking good. Everything's good. Let's uncomment this AprilTag dock. Okay, I think we're good here. Save it and close. Okay, let's go over here and build. And clear. Okay, now let's try to run everything. Oops. Looks like we got a quick error in here. Caught exception in launch. Lib executor docking does not exist. Okay, let's just check and see our CMake lists. Maybe we've got some issues. Yeah, boom, ROS master. Yeah, boom, ROS master docking. Get it CMake. And let's have a look. Okay, we've got our executable added. Emit target dependencies. Oh, I see the issue. I forgot to add the install target. So install, make sure you add this, folks. Open parentheses, targets. And then next line. And then we need detected dock pose publisher. Okay, and then destination, lib /$ curly braces, and then project _name, curly braces. And then go down here, close parentheses. So install targets detected dock pose publisher, and then destination lib project name. All right, so that should do it. Let's save it. Let's build again. Let's build over here. All right, let's clear, and let's try to run again. Looking much better. So that install target needs to be there. So the executable is being built, but wasn't installed in the correct location. That's why we had to add that. Wait for everything to come up. Okay, it looks like everything's up. So let's go over here to the terminal. Let's set the pose. Set the pose. Okay, and once we have set the pose, let's move the robot around to the dock. So I'm going to click the Nav2 Go button, and let's set this to look at it. Go over here. turn this around. Zoom in. And let's angle it a little bit more so we can actually detect the dock. Okay, so we should be able to see the dock now. All right. So I'm just going to clear that. Let's do this just to verify. I just want to verify that the tag is in the image. So I'm going to do ROS2 run image view space hyphen ROS hyphen args space hyphen R image, and then assignment, and then cam underscore 1 color image underscore rect. Yep, right in the center. Absolute perfection. Right in the middle. I love it. Okay, so let's clear. And let's have a look at the detected pose topic. We should see a publisher and a subscriber. So ROS2 topic info, detected dock pose space -v. And we should have a publisher, which we do, and a subscriber, which we do. And let's have a look at the detected dock pose. ROS2 topic echo detected dock pose. Yes, my friends, we have it. And the position information even makes sense because the position right at 0, okay, relative to the camera optical frame, because the tag is right in the middle of the camera frame. Y0, so Y0, we should expect the tag in the bottom of the camera frame, which is correct, in the positive Y direction, which is down, okay, increasing as we go down, so 0.2 meters down. That's correct. And then the wall is about ½ a meter away from the camera optical frame, which we can confirm by looking at the RViz. Yep, about ½ a meter here. About ½ a meter right there. Okay, because each of these squares is 1 square meter. So 1 meter between here. So that's about ½ a meter. So the pose information is correct. And if we go here, just Control C, we got 0, 0.2, and 0.5. 0, 0.2, and 0.5 for X, Y, Z. Let's see if this matches with the transform data. So ROS2 run, TF2 underscore ROS, and TF2 underscore echo. And then we do cam1 depth, optical frame, and then tag 36H11, and then 0. Misspelled. Okay, so cam1 depth, optical frame. There we go. We have 0, 0.2, and 0.5, which matches up perfectly with the information we had in the pose. So we are all good there. Close everything down with Control C. Now that we have the data set up, it is time to configure the docking server for Nav2. The docking action in Nav2 guides your robot from its current position to a successful connection with the charging dock. Here's a high-level overview of how it works. First, the action server receives a request to dock, either specifying a dock ID from a known database or providing explicit dock pose information. Next, if the robot isn't already near the dock, it uses Nav2 to navigate to a predefined staging pose near the charging station. Once at the staging pose, the robot begins to search for and detect the AprilTag associated with the dock. Then, using visual feedback from the AprilTag, the robot enters a precision control loop, carefully maneuvering to align itself with the dock. The robot continues its approach until it detects contact with the dock or confirms that charging has begun. If the docking attempt fails, the system can retry the process a configurable number of times. Then finally, throughout the process, the action server provides feedback on the current state and elapsed time. This structured approach allows for reliable docking across various robot types and environments, with the flexibility to handle different dock designs and detection methods. The undocking action in Nav2 guides your robot from a dock position to a safe staging pose away from the charging station. Here's a high-level overview of how it works. First, the action server receives a request to undock, optionally including the dock type if not already known from a previous docking operation. Then the system verifies the dock type and current docking status, ensuring the robot is actually docked. Next, for charging docks, the system first attempts to disable charging before any physical movement begins. Then once charging is disabled, the robot calculates its staging pose based on its current position relative to the dock. Using a precision control loop, the robot carefully maneuvers to the staging pose while maintaining specified linear and angular tolerances. The system monitors both position and charging status, only considering that undocking successful when the robot has reached the staging pose and charging has completely stopped. Throughout the process, the system enforces timeout limits and can respond to cancellation requests for safety. Now, this structured approach allows for reliable undocking that works across different robot platforms and dock types while maintaining the safety and integrity of both the robot and the charging equipment. To use the Nav2 Docking Server, you'll need to create a database of known docking stations in your environment. This database will tell your robot where docks are located and what type they are. Here's how to set it up. We'll store our files in the Yaboom ROS Master docking package. And by the way, just while I'm at it, let's go to Google here. And I want to show you, let's go to Nav2 Docking, GitHub. And I just want to show you this. Nav2 Docking. So you got a complete guide here. Your complete guide. Look how beautiful that is, docking. Way to go, Steve McKenzie. He's the developer of this navigation stack. But here is your full guide about how to set up the docks, how to get the whole environment, databases, and docks set up. But we're going to walk through the process now, just step by step for a simple dock at the AprilTag. Okay, so we've got a terminal window open, and let's go cd source, cd Yaboom ROS Master, and then cd Yaboom ROS Master docking. Okay, clear. Let's do cd config. All right, and let's add let's do touch dock underscore database dot YAML. Touch dock database dot YAML. So to get it, dock database dot YAML. And let's go over to our repository to see what we need to put in there. Docking config. And let's open this puppy up. Okay, Control A, Control C. Okay, and remember, follow along with me, click by click, keystroke by keystroke. So here are our lines. So we got the type of the dock, the frame, and the pose. And then save. And close. So in this file, that YAML file that we have, let's do cat dock database dot YAML. So in this file, we have the unique identifier, which is dock0, the type of the dock, okay, the pose, position in XY, and then the theta, position, okay, pose of the dock, and then the coordinate frame, in which the pose is located. So that's how you create the dock database file. And for more instructions, you can go to the GitHub, but this is just for a single simple dock. Okay, now let's clear. cd dot dot, cd dot dot, cd yaboom ROS master navigation. We need to configure the docking station now with our navigation parameters. So cd config, get it ROS master. And let's see where we need to go here. Go down to the docking server right here, which is down on line 411. Okay, and here are parameters. And I'm going to go to Google. So you can have an understanding. So docking server, Nav2 parameter guide. So you can see what all the parameters are. And stand for, you go to this URL, and that'll give you a complete description of what the parameters mean. But we're going to just do it. So docking server parameters in our navigation file, and I think everything is already set up. Only thing we need to uncomment here is this line on line 448, the dock database, which we just added. Let's see if we need to uncomment anything else. I think everything else is fine. So this tells navigation where your dock is located, defines the type of the dock, okay? And then the dock database contains the information about the dock. So let's see. Okay, I think everything is okay. Okay, so save the file and close. That's all good. Let's close. And let's build. Alrighty. Okay. Okay, now let's send the robot to the dock using RViz. So I am going to build once more. Clear. And launch navigation, NAV. Okay, and let's set the pose. Okay, now let's take a look at the right panel. This is what we're going to use, the docking plugin for RViz. All right, and you can see it right here. And in the dock ID field, we're going to type dock 0. Just like that, dock 0. This is the ID of the docking station. And next to the dock type, click ROS Master X3. Okay, and then once that's done, click Dock Robot. And now we're navigating to the staging pose right there. You can see nav to staging pose. And we're now active. We're waiting for reached. You can see the state controlling. Initial perception. Okay, and now it says reached. And if you look in the terminal, we can see all of the different logs right here. So it attempted, it failed for a second there, it then returned to the staging pose, attempted again, various attempts. Okay, and then it failed, and then it tried several retries, and then it finally, on the last attempt, it made contact with the dock, and then it said waiting for charge to start. And then robot is charging. Okay, and I just created simulation of charging. All right, and let's go over to the Gazebo to see where the robot is. Let's turn it around. Okay, and let's zoom in. Let's see how we're doing over here. Zoom in. Oh, isn't that beautiful? Right at the charging dock. Right at the charging dock. Right in front of the ArUco marker. Man, that is gorgeous. Perfection in docking. Right at it. So by the way, instead of using the RViz plugin, another way to have docked would have been to use this command. Okay, and take a look at that command there. You could have also typed this in the terminal. So ROS2 action, send goal, okay, to the dock robot action server. The message type, the action type, and then all the information we need. So use dock ID, add the dock ID, the dock type, the staging time, and then navigate to pose. Navigate to staging pose first, true. We set it to true because we want the robot to use ROS2 navigation to navigate to a staging pose that is directly in front of the dock. So we could have used that. So just remember that command. Okay, now we've got RViz and Gazebo open. And by the way, sometimes over here in the state, you might have a state that says wait for charge. That's totally fine as well, where it says reached. But just make sure it says reached, okay, when it gets to the charging dock. And now to undock the robot, we need to open a terminal window. You could use the button on RViz, but I find it a bit finicky. It doesn't always work that well. So let's go and do this. Here is the command. So let's go here. And by the way, I should just mention, so when you run this command to undock the robot, all right, you can put this to 30 seconds to give it 30 seconds to undock. But I had a lot of issues with that. I really did. I think this is still a very new package, this docking server, and I had quick aborts when I tried to undock. So what I like to do is shorten the max undocking time to 2 seconds. I had better results with this. So let the action abort. So you set it to 2 seconds, let the undocking action abort, and then send a regular navigation goal after that. So again, this package is fairly new and it definitely needs a little more work to be ready for prime time. So let's go here and show everything. By the way, I want to show you the robot. Let's go over here into Gazebo and zoom in. Look at that beautiful docking. Okay, so robot's at the dock. And we can see it on RViz. And now let's do the undocking. I want you to see the terminal and RViz at the same time. So watch this and press enter in the terminal. Okay, goal accepted and goal aborted really quickly. That's what we expected. So all we did was just move off the charging dock. And it aborted really, really quickly. And then you can send a navigation goal to wherever you want. Now the robot's going to go out. That's how I found the best way to deal with that, is to just let it abort, push it off the dock using the undocking action server, and then send a regular navigation goal. Again, folks, the docking server is new, and if you want, you can hire me. I can help you do Simple Commander API to develop a custom docking node and undocking node, which will enable cancellation in the middle, and you have a lot more control over what's going on. But this is how you would do it. Use the Nav2 Docking Server. There'll be a time in the future where I'm sure this is ready for prime time, but it's very finicky now. Yeah, try to dock the robot again. Let's see what happens. Just give it a redock. Let's see what happens if it gets to the dock. See if she finds it. She should come in any moment here into RViz. Okay, and it thinks it's at the dock, but it's a long way from the dock. And that is the issue. So that's the finickiness of it. The redocking is not so clean. And I see, yeah, it says it robot's charging, but clearly we are not charging. We're a long way from the charging station. So again, everything up until really the AprilTag detection, detecting the pose and getting the detected dock pose, everything translates to your own application. It's the actual process of docking, the docking server, which I really like to use my own custom node for that rather than the Nav2 built-in docking server, which is, again, very new as of ROS 2 Jazzy. Maybe it was added in Iron, I don't remember, but it's new within the last, as of the date of this video, it's new as of the ROS 2 recent distributions. So I always use my own custom node for my own real-world robots. So that's it for this tutorial. We've covered a lot of ground. You now know how to dock and undock and Nav2. Thank you for watching and keep building.